Thank you, Mary. So my career spans almost 50 years, and I worked on a variety of different computer science topics during that time. And this graphic is a fun thing that my colleagues at Microsoft Research did when I retired from MSR 2 years ago. And it kind of describes my career down over in the lower left part, the Gulf of Academia. I spent the first 17 years in academia, and then the rest of my career was in various industry research labs. And most of my work was concentrated on user interface research and information visualization, which is those two islands you see, and kind of bouncing back and forth between those two. So I actually purposely was being flexible in what I worked on because I wanted to find things that would have really positive impacts on people's lives. And I wanted the flexibility to work on whatever looked like it would have the biggest impact. So in this talk, I'm going to kind of review from very personal point of view the highlights of my career in pretty much chronological order. And I'm going to highlight three things. I'm going to highlight the key people I worked with, the key technologies that I invented or helped to invent, and the principles that came out of that work. So I started in 1965 as a programmer on an IBM 1401, which is what you see pictured there. I was working on a hospital information system at the University of Tennessee, and I was programming in machine language on punched cards. And that machine, it looks kind of big and clunky, but it actually only had 4,000 bytes of magnetic core memory. And the reason I'm showing you that is that obviously technology has been changing a lot. If you look back 50 years ago, nobody at that time had any idea what it would be like now. In fact, there were a few people looking out, guessing what it would be like, and they were totally wrong. So I believe that 50 years from now, things are going to be totally different, and none of us has any clue what that's going to look like. However, as researchers, we have a responsibility to look out as far as we can, and I think we can predict 5 to 10 years out. And one of the things that makes that possible is that the change, even though it's fast, is kind of punctuated equilibrium. That is, it's slow changes for a while and then something happens that causes a big change. And if we can predict those big changes, those technology discontinuities, then we can make real progress. And I'm going to, as I go through the talk, I'll point out several places where I succeeded in being with a group of people that predicted technology discontinuities, and at least one where I thought there was going to be one and it wasn't. So I worked my way through college at Vanderbilt as a systems programmer. And I started out working on operating system design and implementation, and then went into programming language implementation. I built an Algol compiler, I worked on a COBOL compiler, and then I built Lisp on a Sigma 7 and L6 on a Sigma 7. L6 was the Lincoln Laboratories low-level linked list language. And doing those two things, I really got hooked on list processing languages. So in 1969, I went to Carnegie Mellon as a graduate student and then later stayed on as a faculty member. And I worked on a variety of things. The first year I was there happened to be the first year that Raj Reddy was an assistant professor there. And I worked with Raj on building the infrastructure that he needed to do his speech understanding research. And then the second year I hooked up with Alan Newell and worked with him for a number of years. And two major projects I worked on with him were LSTAR and ZOG, which I'll talk about more as we go along. And then later on I worked on Accent and Spice with Rick Rashid and a number of other people. Accent was a kernel-based operating system that was actually the predecessor to the Mach operating system. And the SPICE file system that I built was the predecessor to the Andrew file system that you may have heard of. So Alan Newell was the real reason I went to Carnegie Mellon. I wanted to study under him and work with him. He passed away in 1992, and those of you who had a chance to work with him, I'm sure greatly miss him. I had the honor of working with him for about 13 years. He was my mentor for most of that time, and I learned a lot from him. The first thing he taught me was how to work effectively with a team, and about the value of multidisciplinary teams, especially the importance of working with a cognitive psychologist, which, as you will see as I go along, comes up over and over again. He taught me how to apply the scientific method to computer science research, and maybe the most important thing was to teach me the importance of the user, the importance of understanding the user's task, the importance of understanding the human cognitive and perceptual capabilities and limitations, and human time constants. So in 1970, with Alan Newell and Don McCracken, for about 10 years I worked on L-Star, which was the successor to IPL5, which was an AI programming language that Newell and others did in the 1960s. The name L-Star comes from the idea of applying the Kleene star to list processing languages. That is, we were trying to take the best ideas from all of the list processing languages at that time and put them together in one system. So L-Star was a system for building software systems rapidly. It was kernel-based, and that meant that I could easily port it from one machine to another fairly quickly. It was highly interactive. It was interpreted rather than compiled, although we did have a compiler. And it was highly extensible. It was very easy to build other languages on top of L-Star. So a key principle that came out of this work for me has to do with iterative design and rapid prototyping, which can lead to better system design. Obviously, you need some kind of evaluation metric in order to do the design iterations. Well, L-Star encouraged this approach and, in fact, used the approach itself. So there were 9 major iterations of L-Star as a language and programming environment. Because it was kernel-based, that actually helped with doing the rapid prototyping of L-Star itself. And it also helped to when we wanted to move it onto other machines. I got to the point where I could move it to a new machine in about 1 week. So for evaluation, we did a series of what we called software experiments. And this was actually an early form of user studies. This was in 1971, 72. User studies on programmer productivity, on individual programmers or small teams of programmers. So Stu Card is the second cognitive psychologist that I got to work with, and I actually worked with him on 3 different occasions. The first was in 1972. Al Newell and I built the first version of ZOG in 1972, which I'll talk about in a few minutes. And Stu was one of the first users of that system. And then later in 1975, I got a chance to work with Stu a second time. Stu and Tom Moran had finished their PhDs at Carnegie Mellon and went to Xerox PARC to start a group called Applied Information Processing Psychology. And the purpose of that group was to do user studies and iterative design for Alto applications. And both Stu and Tom had experience with Lisp, and that's what they wanted to build their user studies in, but there was no Lisp on the Alto. So they hired me as a consultant the first thing I did for them was to build a version of L-Star on the Alto. Now, as I said, the L-Star usually took about 1 week to port to a new machine. In this case, it took a little bit longer because I had to build some of the operating system features as part of the port. The second year that I worked with them, I rebuilt the kernel for L-Star in microcode on the Alto and got this totally amazing result, which I never saw before, and I haven't seen it since. The interpreted code for L-Star was actually smaller and faster than compiled code. Well, Tom and Stu did some of their programming in L-Star, but they were really, they loved Lisp, and they wanted something closer to Lisp. So Tom and I spent one of my sessions with them designing a new language called ERL for experiment running language, which was very much like Lisp, and designed specifically for doing user studies. And then I built it on top of L-Star, Alto. So one side note here is that what I learned from Tom and Stu about doing user studies, as Mary mentioned, I took that back to CMU for the ZOG project, and I think it was in 1976, built one of the first user study labs in a university environment. So the first version of ZOG was done in 1972, and Al Newell and Zenon Polishin were planning to host a week-long workshop on cognitive psychology. And they intended to look at a dozen or so demos of various kinds from around the world. And they needed a unified framework in which to study these different demos. So Al Newell and I designed this first version of ZOG, and I built it. It was a menu selection system, one of the first hypertext systems. And if you remember, in 1972, the computer terminals at the time were text-based CRTs. So they were typically 25 lines of 80 characters, text only. And ZOG would provide menus in that context, typically 6 to 10 menu items. And selection was typing a single letter or number. And then there was an action language that allowed executing arbitrary actions, and that's how we ran these demos. And that action language was actually one of the first hypertext markup languages, although that language didn't exist at the time. So a couple of years later, the Department of Health, Education, and Welfare was funding a project at the University of Vermont called PROMISE, or Problem-Oriented Medical Information System. And I was invited to serve along with Al Newell and Ivan Sutherland on the PROMISE Advisory Committee. And we got a chance to visit there a number of times and interact with that group. PROMISE was developed by two key people. There was a physician named Larry Weed and a computer scientist named Jan Schultz. And PROMISE was a rapid response menu selection system. It was done on touch screens, and the response time, the design goal was to have a response of a quarter second 70% of the time. It had a comprehensive frame library or menu library for the task at hand, which was running a hospital. And for them, that was about 30,000 frames. So Al and I saw great potential in taking the ideas that we saw in PROMISE and applying them back to what we had done a couple of years earlier in ZOG. So we built a new version of ZOG that was somewhat closer to PROMISE. It was a rapid response menu selection system, and in our case, we were targeting between a quarter second and a half a second response. We still had the simple selection, so it was either a single character or one touch on a touch screen. We wanted a large, comprehensive network of information, large enough to do whatever task was at hand. We weren't really sure what that meant, how large is necessary. And if you think about it, the World Wide Web is kind of an evolution of what we were thinking about at the time. And currently there are hundreds of millions of pages on the World Wide Web, and it's still not clear that that's comprehensive enough. So who knows what the proper size should be. One of our principles was no sudden death. That is, there should be no irreversible action that you can take without user confirmation. There were a set of universal actions that were available on every menu, things like back, help, home. And there was a communication or action language, which was essentially a hypertext markup language. So, rapid response. The promised design goal was a quarter second most of the time. We weren't really sure if that was optimal. Nobody had done any study to figure out what that timing should be. So we wanted to do some user studies, and we did this on a version of ZOG that I built on C.MMP, which was an experimental multiprocessor that was being developed at Carnegie Mellon. There were two reasons for doing it on C.MMP. One was there was an experimental graphics display system with a touchscreen, and I had access to the device drivers for that graphics display. And there was a zero latency drum, which back at the time, you always had to worry about latency when you were accessing something from a disk or a drum. But this system was designed so it could read a track anywhere on the track, so you didn't have to wait for the start. And also I had access to the device drivers. So I built that version of ZOG essentially to operate at interrupt level, and that meant I could get the interaction to happen faster than 60 milliseconds response time, which meant that I could do user studies everywhere from a 16th of a second up to a half a second, and that's what we did. And we found that for these kind of menu selection tasks, that somewhere between a quarter of a second and a half a second was optimal. So the key principle behind all of this was trying to tune the HCI interaction to human time constants. And this was based partly on theory. Al Newell had been developing this analysis of levels of cognition, which you can find in his book, Unified Theories of Cognition. And he has about 20 levels, and two in particular are relevant. One was around 1 second, which he called the operations level, or unit task times. And the other was around 100 milliseconds, which he called the deliberate acts level. And that was for pre-existing actions. And our user studies showed that the optimum was between a quarter second and a half a second, which actually fits the theory quite well because the simple menu selection is a simple unit task. So it ought to be toward the low end of his operations level. So in 1982, Navy Captain Richard Martin, who was the commander of the USS Carl Vinson aircraft carrier, which was under construction at the time, came to us and wanted us to put a distributed version of ZOG on the aircraft carrier for two purposes. One was to run the ship's organization and regulation manual, which is what every department in the ship used for their day-to-day operations. And he also wanted to put the aircraft elevator maintenance manual in this system. And this is actually quite important because if you think about it, the aircraft elevator on an aircraft carrier is actually the biggest piece of equipment on the aircraft carrier. So keeping it functioning is critical to the task of the aircraft carrier. And to do that, we actually extended ZOG to a hypermedia system by adding video disc players to the system. And this version, because he needed a distributed system, we re-implemented ZOG on a network of PARC personal computers. So, shifting gears, in 1982, for a couple of years, I was at Bolt Beranek and Newman as a senior scientist. I worked primarily with Bob Thomas and Harry Forsdick, and we were working on the Diamond multimedia mail system, which was the first multimedia mail system. And you have to remember back to 1982, all the mail systems at that time were text only. And to do this, we built a multimedia document editor as the basis for the mail system, and this supported text, graphics, images, audio, spreadsheets, and charts. And we had an editor that had integrated editing capabilities for all of those media types, something that even modern multimedia mail systems don't have. If you think about it, there's no audio editor in any of your mail systems. So here's a sample of a Diamond document. This one has text, audio, a graphic, and an image. And notice right up here, the audio is represented by a little icon. If you clicked on that and your workstation had audio capabilities, they would just play it the way you would expect. But only about half of our workstations had audio. This was at a time when it wasn't clear that workstations were going to have audio. So if your workstation didn't have audio, our system would actually call your office telephone and play the audio or record audio over your telephone. Very clever but simple solution. So a key principle here has to do with what I call time machine computing. We were exploring a potential technology discontinuity because doing Diamond the way we did it was quite expensive. We were on a network of Jericho personal computers, and each of those computers at the time cost about $30,000. And we had the firm conviction that eventually that kind of computing would be cheap enough that everyone would have it, but that was going to take a while. So by using expensive hardware at the time, we were able to explore multimedia mail well before it was affordable to do. So between 1984 and 1988, I was a senior scientist at Thinking Machines, and here I was exploring what I thought might be another technology discontinuity. I was working on the Connection Machine, which was a massively parallel computer. It had 64,000 processors, and I worked on a number of different applications as well as some of the basic hardware and software architecture design issues. It was all very interesting work, but it did not lead to a technology discontinuity. So fortunately, I was rescued from that by Stu Card for my third time working with him. And this time I worked very closely with Jock McKinley as well. And I was hired to work on an intelligent information access project. And this very quickly turned into the first information visualization project, or one of the first projects like this. And it was motivated by two principal things. The first was the scientific visualization field got a big push in around 1985 with some NSF funding, and the first thunderstorm visualization was done around that time. And this was using 3D animation to show a simulation of a physical process. And what we wanted to do was to use that same basic idea but apply it to more abstract information, like the relationships between documents or people. The second thing that was driving us was a couple of theories on cognition and perception. One was Alan Newell's analysis of levels of cognition, and the other was Sheridan's supervisory control theory. And that actually led us to the design of the cognitive coprocessor, which was our animation framework in the information visualizer. And we presented that at WIST 1989. That paper, by the way, is where we first introduced the term information visualization. We were actually predicting a major technology discontinuity here because the work we were doing at the time and also the work the scientific visualization community was doing was on very expensive silicon graphics computers. And these computers certainly enabled 3D animation and interactive animation. But we had a firm belief that that kind of computing, it cost like $250,000 for one of these computers, would come down maybe in 5 years to the place where it would be a commodity item and most people could afford it. We were off by a little bit. It took about 8 years rather than 5, but we were dead on in our prediction. So the first 6 months that I worked for PARC in 1988, I was working out of my basement in Marblehead, Massachusetts, and I had one of these $250,000 irises in my basement. It's got to be one of the most expensive personal computers that's ever been. And during that 6 months, I built the first version of Cone Trees and the first version of the Information Visualizer framework. And then in November of that year, I moved to Palo Alto, and this is an interesting side note. I think the first day I was there, John Seeley Brown, who was the director of PARC at the time, came into my office and saw a demo of Cone Trees and this first version of the Information Visualizer, and he was so excited by the work that he really wanted us to keep quiet what we were doing until we had developed it a little more and filed a bunch of patents. So 2 things came out of that. He insisted that I reorient my office so that people walking by my office couldn't see what I was working on. And he also kept us from publishing what we were doing for a couple of years. At CHI 1991, we published 3 papers that were presented in one big session. And we could have published that 2 years earlier, except that the leadership at PARC wanted us to hold off until we had filed a bunch of patents. So we continued that work for about 8 years, building a wide variety of different visualization techniques. One of the first problems we had to solve was that we were in a 3D environment, and at the time, navigation in 3D environments was pretty awkward. You were shifting between different modes, and you often overshot your target. So we built point of interest navigation. This is work that Jock and I did, and Stu contributed to. And we introduced this at SIGGRAPH 1990. So the basic idea is you identify an object of interest and then a point on that object that you're interested in. And then with a single action, you fly toward the object and toward the surface normal of the object. So you're following a path like that. And we used a logarithmic approach function, which meant we went very fast at first so you could cover a lot of distance, but as you approached the point of interest, you would slow down so you had fine control, and you've never overshot your target with that. So we were taking a difficult 6 degree of freedom manual control theory problem and turning it into essentially a point-and-click interface. So key principles here, we were using interactive animation to engage the user. And what I mean by interactive animation is that some user action initiates an animation sequence, and they would be like transition animations or navigation animations. Second, we were supporting multiple agents. This is part of Sheridan's supervisory control theory and what we did in the cognitive coprocessor. So essentially the animation loop was separated from other agent activities. For example, if you did a search, you could still interact with the system while a search was going on. You didn't have to wait for the search to complete. The third thing had to do with task management. A couple of years earlier, Stuckart and Austin Henderson had developed the Room system, which was a a task management system. And we extended that idea into the 3D environment. So each 3D room had the objects in it that were necessary for whatever task you were working on. And then task switching was walking through a door into another room. And finally, we did constrained 3D navigation to simplify the control problem. That's the point of interest navigation. So code and trees was the first visualization that I did in the information visualizer. And we published this at Chi 91, but as I said, it was actually working in 1988. The idea was to use a focus in context display so that you could always see the global context while you're focusing on the details. We were doing this in 3D because we wanted to get more information in the same amount of screen space. And we wanted to be able to see more of the structural relationships. So the idea was when you click on a node, the tree would rotate around, each of the nodes would rotate around, so that the selected node and the path to the root was in the front of the tree, and that was your focus. And we did this with a 1-second transition animation. I'm going to show you a quick video. This is really old video, so it's kind of grainy. You're going to see 4 selections. The first 2 are without animation, and you'll see that when that happens, things change, but you're not quite sure what happened. And then the second 2 are with animation. So here's the first one, things changed. And what am I looking at? And here's another one, things changed. And here's one with animation. And with that 1-second animation, you can track what's going on and you don't have to think about what you're looking at when it's completed. So in early 1989, Jock McKinley and I started building the perspective wall, which was designed to show linear structures like time relationships. And the idea here was when you selected a node on the wall, it rotated around with a 1-second transition animation to bring the selected node to the center of the front panel. And doing it in 3D allowed us to get about 3 times more context than we could in the equivalent 2D view. And one thing I'm often asked about is if you look at the papers we published throughout this 8-year time period, we weren't doing any user evaluations. And I'm often asked, why didn't we do that? And the answer was Stu had a very firm conviction that it was premature to do that for 2 reasons. One was we were doing something quite different from anything else that existed at the time, so we didn't have anything to do a comparative evaluation with. And the second was that he thought doing feature-based usability studies would be misleading, that you needed to look at the larger picture. So we put off doing any user studies. So key principles in this work. First was focusing context displays. It makes it easier for the user to understand the context of the information being worked on. The second was using transition animations to help the user retain the context during a view change or a transformation of some information or structure. And the third was tuning to human time constants. As I said, all of our transition animations in this system were 1 second. They were slow in, slow out animations, so it focused on the start and ending point, which were the most important, where the most important information was. And they were all using constant time animations. Now, if you think about it, the systems back at that time, most of them were using constant rate animations, which was much easier to implement. But we knew we wanted to match the human time constant, which meant we had to have constant time. And then finally, the advantages of 3D over 2D. I'm often asked about this because about half of my work was in 3D and half was in 2D. And my answer is that as long as the spatial relationships in the information are important, then 3D has an advantage because you can get more information in the same amount of space and still convey all the information you want. And this was borne out again and again in all of the work I did at PARC and much of the work that I did at Microsoft Research. So a side note about conferences. The first information visualization papers were those three that we did in CHI 1991. That was in the spring of 1991. In the fall of 1991 at the IEEE Visualization Conference, Ben Schneiderman presented tree maps. And those two events, CHI 91 and Visualization 91, kicked off a lot of work that started happening in universities and industry labs over the next few years, and it's still going on information visualization. And between 1991 and 1995, most of the papers were being published in either CHI or WIST, and a few of them showed up in IEEE Visualization. And then in 1995, we held the first IEEE InfoVis symposium in conjunction with IEEE Visualization. And that eventually grew into a conference in 2007, and it's now the primary venue for information visualization papers. But it's important to note that CHI as a community helped give the field of information visualization its birth and its early nurturing. So in 1996, I joined Microsoft Research, and Mary Truinsky was my key collaborator through that time that I was there. There were many other collaborators that I had there. When I went there in 1996, I was managing a user interface research group, and I was encouraged to build my dream team working on whatever I wanted to work on. And of course, I wanted to continue working on information visualization. And I knew that dream team had to be multidisciplinary, and I knew it had to have a cognitive psychologist on it. So Mary was the first person that I got on that team. And then we continued to do a lot of exciting research over the next 15 years or so. And Mary and I have co-authored about 35 papers. So we worked on a variety of information visualization techniques. Broadly, they're in these 5 major categories: business visualization, information management and exploratory data analysis, software productivity, entertainment, and homeland security. And those, the names you see up there are a sampling of some of the projects we did over that 15 years. And I'm going to pick a few of those to go into more detail. They're kind of the systems that I have the fondest memories of. The first is the Data Mountain, which we presented at WIST 1998. This is doing document management on, conceptually it's on the side of a mountain. In the prototype, it was a tilted plane, and that's what you'll see. The idea was that when you selected a document, it would fly out towards you and bring it into focus, and that was with a 1-second transition animation. And we tested this as a replacement for the Internet Explorer favorites mechanism. Pages of interest were placed on the mountain, and the act of placing a page would help you remember where it was. The subjects in our studies tended to group pages together by topics, although there was nothing dictating that. It just was a natural thing to do. So every subject had a different grouping. But that didn't matter. It was what made sense to the user. And we did a series of user studies. We were looking first at timing. So we did storage and retrieval of 100 web pages and found that the Data Mountain was about 26% faster than IE favorites for retrieval. And then we did 2 really interesting studies. One was we brought some of our subjects back 6 months later and tested just the retrieval part. And it turned out they had exactly the same performance. Some of them were even faster than they were 6 months earlier, which tells you that the spatial memory that we were using actually is quite long-lived. And second, we weren't entirely sure that it was all spatial memory that we were using. We thought maybe the images were helping. So we did one study where we would alternate between showing the images as normal and then showing blank pages. And it turned out the subjects, after they got over the shock of seeing these blank pages, they were just as fast with or without the images. So it's definitely spatial memory that work here. And here's a brief video that shows what this looks like.
The Data Mountain is a first-generation prototype of a 3D user interface to store and retrieve documents. In the prototype you see here, all documents are web pages, making the Data Mountain an alternative to Internet Explorer favorites or Netscape Communicator bookmarks. Our goal is to leverage the human abilities of spatial memory, pattern recognition, and 3D perception. Note that the documents on this inclined plane are smaller toward the back, that objects occlude each other, and that they cast shadows on the ground plane. We observed from gathered data that few users have more than 100 favorites, and that they do not often employ nested folders to organize their favorites. The prototype supports this informally. The ground plane texture has landmarks meant to suggest simple groupings, but these are only passive markings, not grabbable groups. Here, the user has decided to save the current web page in his or her favorites list. By dragging the page, the user can place the new page anywhere on the Data Mountain. Previously placed items can be moved as well. Note that even though the Data Mountain is a three-dimensional object, users can place pages with an ordinary mouse using a simple 2D dragging technique, since the space is an inclined plane. We get the advantages of 3D visuals without requiring an unfamiliar 3D interaction technique. The Data Mountain prevents users from placing pages very closely together by enforcing a minimum distance between pages at all times. This is important to keep users from losing access to documents due to total occlusion. This displacement technique has been designed to give continuous feedback on the state that will result if the user releases the mouse. If the user moves on, pages move back to their previous position, but when the mouse button is released, pages take on their displaced positions. This creates a very predictable behavior. Clicking on a document brings it forward for inspection, and another single click returns it to its prior location on the Data Mountain. The Data Mountain displays tooltips for each thumbnail to allow quick inspection of document titles. A matching halo around the thumbnail helps identify which page the tooltip is for. The Data Mountain plays subtle interactive audio cues to enrich interactions.
The audio is actually turned up louder than it
the audio
normally
is spatialized to enhance the sense of 3D space.
So the key principles we're exploring here, first we're using 3D perception and spatial memory to help organize and retrieve these documents rapidly. And we're able to, as I mentioned, get more information in the same amount of space by using 3D with no added cognitive load. So we're getting the advantages of the 3D visuals, more information, but we're still using 2D interaction techniques. We minimize user navigation by bringing the information to the user rather than forcing the user to navigate to the information. And then the subtle audio cues. People were giggling about that. We made it intentionally louder so that you could hear it on the audio, but they were pretty subtle. And this was work I did with David Thiel. And interesting side note, we did at least one user study where we tried to figure out exactly what benefit we were getting from the audio. And we didn't see any performance advantage from the audio. But there was clearly something going on because for the subjects who saw the normal system first and then the system without the audio, universally, they thought the system was broken, even though it was still functioning exactly the same. So the audio is doing something there, but we just don't know how to measure it. So when I showed the Data Mountain to Bill Gates, he was really excited by it, but he challenged us to think about how we would replace the Windows desktop with a 3D environment. basically to solve window management and task management problems in 3D. And we had a large enough team that we actually broke into 3 small teams and had a design competition. And then took the best ideas from those 3 teams and put that into one system. And then Martin Van Danzig and I did most of the implementation work. And what we built was the task gallery, which the current task is a set of windows which is on a stage at the end of a hallway. In fact, when you're up close to the stage, you don't know that you're in a hall. And then if you back up, you see that you're in something like a simulated art gallery, and the pieces of art on the walls are the tasks. And switching to a task is just clicking on one of those. And I'll show you a quick video of what that looks like.
The Task Gallery is a 3D window manager that addresses 2 key problems with current window managers: task management and document comparison. Tasks are collections of windows relevant to a particular user activity. They are represented as artwork hung in a virtual art gallery. The Task Gallery hosts unmodified Windows applications by redirecting both their input and output. The primary working view is a close-up view of the stage at the end of the gallery, looking at the current task and its live windows. A user switches to a new task by clicking on it. The windows associated with the current task are replaced by a snapshot which is moved back to its original frame in the gallery. While that is happening, the newly selected task is moved from its frame to the stage. When it arrives at the stage, it is transformed from a snapshot into live windows. Tasks are moved around with a simple dragging movement and are constrained to remain on the walls, the floor, or the ceiling. In the user's left hand is a start palette with icons for accessing applications and favorite documents. Selecting an object from the start palette launches an application with its windows in the current task. Picking the new task item on the start palette creates a new task, which is placed on the floor in front of the stage. Multiple windows can be selected for simultaneous viewing simply by using Shift Select on each window. An automatic layout animation moves the windows so that they are all visible side by side. From our user studies, we know that users are honoring spatial properties of real-world environments rather than treating the task gallery as simply an interesting desktop theme. We will continue to explore metaphors leveraging users' real-world knowledge in our future 3D environment.
So the key principles here are using a focus and context display for task management, where the stage is the focus area. Using spatial memory for task organization in this case rather than document organization. Minimizing user navigation. The way we did that in the task gallery was to constrain navigation to moving forward and backward, looking left, right, up and down, and going to the home position, which is right in front of the stage. And that simplified the control problem and also prevented people from getting lost. And we did hundreds of tests with this, and no subject ever got lost in this environment. So at CHI 2002, we introduced Polyarchy, which was, at the time, a lot of work had been done on visualizing single hierarchies, but very little work had been done on looking at intersecting hierarchies, multiple hierarchies. And we had a particular problem that we really wanted to solve, which was in the Microsoft environment. There were a bunch of hierarchies around people. There was a management hierarchy, a business unit hierarchy, a location hierarchy. Altogether, there were about 8 different hierarchies. And there was no way to see how these related. So in Polyarchy, we used a 2D visualization for a single hierarchy, and then we would use a 3D pivot animation. You take the thing you're looking at and the new hierarchy you want to look at and pivot around the person that you're focusing on, and then the pivot would come around and replace the the old visualization. And this lets you see, with this transition animation, see the relationships between the hierarchies. One of the key things that we did was when you do a search, we would elide information that wasn't relevant. So, in fact, you can see that here. There are 3 people highlighted, and by eliding the information that's not relevant to this view, you're able to see how those people relate. So the key principles here, we were using transition animations in 2 ways. One was the pivot animation to show the relationships between hierarchies. And then we also used animation when we did that eliding of information after a search to show the minimum information without losing context. Now these animations were done between a half a second and 1 second based on user preference. And we did some more studies to try to understand what the optimum time in this system was. And for most subjects, it was around a second. For experienced people, it was closer to a half a second. That's why we left it up to the user to choose. And as I said, we're showing the minimum amount of information necessary for the task. So at CHI 2005, we introduced the Schema Mapper. This was actually part of a BizTalk product. It was showing 2 schemas, a source schema and a destination schema, and the functional relationships between the elements. And as you can see, this was from the original Schema Mapper. When you scale up to a large schema, it becomes useless. It's just, you can't understand what you're looking at. So we applied a series of visualization techniques to simplify this, make it usable for large schemas. First, we would emphasize relevant elements and de-emphasize what isn't relevant. So in this case, I've selected something on the right destination schema, and it's highlighted the elements in the source schema that are linked to it, as well as the functional relationships that are linked. And we used animated transitions to scroll both of the tree views and the map so that the relevant stuff is all in the center of the screen. And then in the 2 schemas, we elided the information that's not necessary at the moment in order that you could see more of the relationships. And we did a user study on this that compared the baseline, the original system, with 3 feature sets, and got, boy, this was the most beautiful user study results you could ever want. With each added set of features, we got improvements to task time and also improvements to subjective satisfaction. So key principles: highlight what's important, de-emphasize what is not, use transition animations to retain the context, and show the minimum amount of information needed for the current task. At InfoVis 2007, we introduced DynaVis, which was our use of the kind of animation transitions we've been doing in a lot of our work to make charting more effective by showing all sorts of changes with animation. So changing between chart types, adding, removing, or changing data, or sorting data, all was done with animation. And the animation was not just on the location of the information, but also on the shape of the information. So the original version of this I did with Roland Fernandez, and he helped particularly with the shape morphing techniques. And then a later version I did with Jeff Hare, who was as an intern, worked on adding staging and staggering for more complex animations. Here's a video that shows this work.
When analyzing or presenting information using statistical data graphics, it is common to look at a number of related graphs. For example, the viewer of a bar chart may want to switch to a pie chart to view relative percentages, transition to a scatter plot to look for correlations between 2 variables, or drill down by breaking up the data by categories. Animation is one promising approach for facilitating perception of changes when transitioning between data graphics. Using design guidelines motivated by research of human perception, we have developed DynaVis, a system supporting animated transitions for statistical data graphics. DynaVis provides animations for a number of different transition types, including changes of perspective, filtering operations, and viewing changes of data over time. In some cases, changes of value require changing the axis scales. Here we show a sorting operation. Animating everything at once can result in items occluding each other. By slightly staggering the movement of each of the bars, DynaVis makes the sort easier to follow. Here, a bar chart becomes a radial donut chart. By growing the wedges to take up the whole circle, we form a pie chart. We can also perform drill-down operations, breaking up the data further into distinct categories. We can then unstack the bars to view the same data as a grouped bar chart. Of course, we can always reverse the transitions to return to the view we started with. We might want to compare different variables in a scatter plot to look for correlations. Here, we keep the y-axis values as the same as the bar chart, but use the x-axis to show a new variable. Animation is also helpful for showing transformations to the data. Here we show applying a base 10 log transform to the data. Both data and axes smoothly animate to show the results of the transform. Visual encoding such as shape, color, and size could be used to visualize additional data dimensions. To evaluate the use of animation in data graphics, we ran 2 controlled experiments. The first experiment asked users to follow 2 targets.
Okay, so the key principles here are using transition animations to provide significant benefits when changing representation, for example, chart type, when changing scale, when sorting, when data is changing, or when data is added or removed. And then using staged or staggered animations for the more complex transformations actually provides additional significant benefits. So in 2003, Jim Thomas approached me and asked me to help him work on developing a new field which he wanted to call visual analytics. And Jim is an amazing guy who did some really great work. Unfortunately, he passed away in 2010, and he's greatly missed by everyone who knew him. In 2004, Jim asked me to join an advisory committee along with Pat Hanrahan from Stanford, who was representing academia, and Nancy Chenshorf representing the government. Jim had convinced the Department of Homeland Security to fund development of this new field, and the goal was to combine information visualization techniques with various analytic techniques in order to attack much larger problems than the InfoVis community had been attacking, primarily focusing on intelligence analysis, emergency response management, and border security. So our advisory committee picked 30 leading scientists from various fields representing academia, industry, and government, and brought them together for a week-long workshop where we defined this new field and defined a 5-year research agenda for the field. And that led to the book Illuminating the Path. It also led to the establishment of the National Visualization and Analytics Center, and then soon after that there were regional centers created in universities. So these are the major research challenges that we saw in 2004, and this has all gone in great detail in the book Illuminating the Path. I don't have time to go through this, but I wanted to point out to you that even though this was supposed to be a 5-year research agenda, and it's now been 9 years since we did this, there's still a lot of work to be done in every one of those topics. So I encourage you to look at the book for more details about this. So visual analytics research was originally published just at NVAC-sponsored workshops and symposia, and then in 2006, the first IEEE VAST symposium was held. VAST stands for Visual Analytics, Software and Technology, and it was part of VisWeek. And VAST has now become the primary venue for this work. So I'm going to conclude with some general lessons that came out of my career. The first has to do with mentoring, which was really important to me and when I was being formed as a scientist. If you're a junior in the field, I really encourage you to find a good mentor and learn everything you can from them. And if you're senior in the field and you're not mentoring someone, please make yourself available as a mentor. Second lesson is about collaboration. Throughout my career, collaboration has been absolutely essential. I've had 147 different people as co-authors on papers, and 9 co-authors have published 10 or more papers with me. Those are Mary Truinsky, Stu Card, Jock McKinley, Bongshin Lee, Alan Newell, Greg Smith, Don McCracken, Desney Tan, and Dan Robbins. And note that 3 of those were cognitive psychologists. So another lesson is that I've found that building and working on multidisciplinary teams is really essential, and that having a cognitive psychologist on that team is really important either for information visualization or user interface research. Third thing is about technology discontinuities. We should all be looking for those. And for me, it meant being as flexible as I could in what I was working on, because if I saw a potential discontinuity, I wanted to dive in and see if it was real. And then finally, and I think this is true for everyone here, it's important for us to pay attention to the user. We really are doing this because we want to make a difference in people's lives. And to do that, we need to understand their task. We need to understand their cognitive and perceptual capabilities, limitations, and the time constants associated with those. And we need to tune our technology to those. So finally, I want to thank all of my collaborators over the years, and I want to thank you for your attention. And if there are any questions, please go up to a microphone and.
Yeah, I think that many of the examples you showed have not quite made it into, I guess, mainstream software, mainstream user interfaces yet. And I wondered if you had an explanation for that. And particularly the data mountain, I thought was, first of all, Bill Gates liked the demo, I liked the demo, this might be even harder. And you have data to show that it's much better. And it didn't seem to be that demanding in terms of technology. So why have these things not really taken off yet in mainstream software?
I wish I knew the answer to that question. That particular one, the data mountain, was really interesting because we had all of this evidence that demonstrated that it was better, and we took all of that to the product group, and the key person in that product group at the time simply looked at our data and went by his intuition instead, and he said, I don't believe it. And what can you do if you run into someone like that? So we just kept plowing ahead. One thing you might notice in our work at Microsoft Research was that I kept alternating the projects between something that was focused on a particular product and then something more general. I kept trying to find the way to answer the question you're posing. So another possible answer is with the polyarchy work. I was having trouble getting the 3D work accepted by the product groups. So polyarchy seemed like a very kind of subtle way to introduce 3D without it being really in your face. And that was one of the reasons I took on the polyarchy product. And that one actually was supposed to come out in product form. It was actually out in beta form at one point and then never got shipped, and I don't know why. The Schema Mapper did get shipped. So if you're a BizTalk user, you do see the work there. But none of the work that we did at Xerox PARC ever made it out into any real products that I know of. Except, I'm sorry, that's not true. The Insight was a spinoff from Xerox PARC, and they did provide some of our visualizations in their products. So, other questions?
So this is Feng from Microsoft Research. Really enjoy your talk, George. A lot of things you said, the insights, and they're simple and yet very powerful. The time, the human time constants and such. I worked at the thinking machine, the TMC, in '87. So I still remember that for those machines with 32,000 nodes, the simple way to visualize the computation over that black cube box with the processor laid out was to look at the ways that these lights, the LEDs were blinking. I don't know if you remember. Oh, yeah. I was in the scientific computing group where we were doing this very large matrix computation. And when you do these different row and the column and the SVD computation, you actually simply just looking at the LED blinking and see whether you actually missed a column or done this order in a reverse way. So it was very interesting. One question I have is, these days we heard about the big data, the information, and these billions or trillions of rows of data or columns of data, and the ability to actually look for insights very quickly and to drill down. So I wonder for those of us, whether you have any advice or insights as to what we should look for, what sort of things we should actually focus on.
Yeah, that's actually part of what's driving the visual analytics field. They're essentially taking analytic, in some sense, data mining techniques to take really huge collections of data and get it down to a small enough set that you could then use visualization techniques to do the final steps in understanding what you want to do. So I think that the answer is something like that, a combination of analytic techniques to narrow down the amount of data you look at, and then visualization to finally make sense of what you're looking at.
Thank you.
Hi, George. Gregory About from Georgia Tech. I have a comment or favor to ask of you, and then a question. One is this comment/favor. It always impresses me when I come to these lifetime talks, the amount of contribution I am unfamiliar with for these giants in our field. So I really appreciate the fact that you went through chronologically the things you've done, because many things there that I wasn't aware of, particularly prior to you going to PARC. And so this is the favor I'm asking you, and maybe this is something someone else could do, but an autobiographical account of your accomplishments would be very valuable for us to be able to give to, you talk about mentoring, to teach people to appreciate the history of our field, and being able to, not too many people are here, unfortunately, and I think they miss out on knowing this. And I think this is something to all the more senior luminaries. It would be very useful for us to have a copy of that so that we know what's going on, or what has gone on. The other thing is, I'd like, so that's a favor, so please do it. The second is, I'd just like you to comment a little bit on your transition from academia to industry. And do you think, why you did that is one thing I'd be interested in finding out, and what you think the real differences and opportunities are. You probably can't talk about academia as much now, but I'd just be interested in your insights about why you made that transition, and would you do the same thing today?
That's a good question. One of the advantages I had was that when I was in industry, except for the work at BBN, which was more like, at the time, it was more like contract government work. But the work at Xerox PARC and at Microsoft Research, those actually feel more like academic environments, except you don't have to do funding proposals. So you have more flexibility in what you work on, but they're large enough groups that they had lots of interesting talks. I mean, it felt like an academic environment.
But you don't mentor young students as much.
Well, you do. You don't for over longer periods of time, but you do get a chance in both of those environments to have interns come through on a fairly regular basis, and you do get to work with younger people in, intern-mentor relationships. So you do get some of that.
Well, but I noticed in your list of collaborators, none of those
Published the most with, that's true, because the interns that we worked with, I might have 1 or 2 papers with, whereas the longer-term people I worked with have many more papers with, that's why. But I did have, of those 147 co-authors, a number of them were interns, definitely. Martin.
Hi, George. I wonder what technology discontinuities you think are promising for work for, say, the next 10 years?
That's a good question. I think one of the big ones is one that's already been mentioned, that we're getting larger and larger disk storage systems, and we're starting to look at larger and larger problems. And in the information visualization community, we have tended to focus on relatively small problems compared to what's actually possible to look at now. So I think that's the combination of improved disk storage technology and improved networking technology, the internet speeds, is going to make it, I think that will be a discontinuity, and we'll be able to get access to much more information, and we've got to make sense out of that information. Yeah, that's one. Yes.
Hi, I'm Hillary Hutchinson from Google. So I was really impressed in your talk at how you seem to have this great depth. On the one hand, you're like programming in COBOL, and on the other hand, you're in operating systems and that end. And on the other hand, you're very much into the sort of psychology and perceptual visualization, human eye, that sort of thing. And that kind of depth is something that's really hard for students to get in the HCI programs that are sort of available today. Maybe they get depth, but they don't get, or they get breadth, but they don't get depth. So I'm wondering how much of your success you attribute to sort of your foundational learning in school, and how much of it was really this collaboration that you're talking about, the importance of having collaborators in multidisciplinary fields, and how we can facilitate more of that as we're bringing more junior people up in the field and getting more people who are able to give presentations like this where they're really covering the whole breadth of bringing all of those different parts together.
That's a great question. I think one of the reasons I think it's really important to be, there are 2 reasons I think it's important to be developing and working on multidisciplinary teams. One of them is to address exactly the question that you're raising, that if you're on a multidisciplinary team, then you don't necessarily have to have all of those skills because you're interacting with people that have the other skills. And the other is that, of course, you're going to pick up some of those skills as you go on. The other reason that it's important to be on multidisciplinary teams is that you get all of these different viewpoints about how to solve particular problems. And I think the creativity that comes out of having these different viewpoints is really incredibly powerful. Yeah, in terms of the education system giving you the depth, that's a real challenge. I don't know how you address that other than trying to get yourself onto a multidisciplinary team.
Jeff Johnson. About 10 or 15 years ago, there was a panel at CHI on innovation, and one of the panelists was George Furness. And I seem to remember him making a statement about the difference between innovation and dissemination. And he was he gave an example about how, for example, the desktop metaphor had been sort of invented by Engelbart and then Xerox PARC and then Apple, but disseminated by Microsoft. So he sort of said, Microsoft is good at disseminating things that other people have invented, And so, and all of these, he was saying that he wasn't trying to put down dissemination. He was trying to say that's really important. It's important to disseminate. And it seems that what we have here in several of the questions have to do with the distinction here in your work between innovating and disseminating. Like, for example, I'm a consultant. I consult around the industry a lot, and many of my clients have problems that would be solved by many of the technologies that you've invented. So, for example, many of my clients do system management, server system management, and they have these very primitive, they tend to have these very primitive little graphs that show them, all of their servers. And the problem with many of those systems is that they were designed by interns coming into, let's say, a software company and designing a very primitive graph mechanism. But the problem is the clients, the companies, have not 25 servers, but 25,000 servers. And it does not, these things lock up. They just, not only do they not allow them to visualize everything, they don't even run. You can't even get a display to show up in any reasonable amount of time. And so what I'm wondering about is how do we get, I mean, you were working for a long time at the company that's really good at dissemination. So we've got to figure out in this industry how to not only innovate, but also to disseminate.
Yeah, I agree. There's this also goes back to Jacob's question earlier. One of the things that I've heard said many times is that the average amount of time it takes to get from the creation of an idea to it actually being disseminated into the field is something like 17 years, which seems astounding with how fast things go on in the field. And much of my research has been kind of on the cutting edge, which kind of naturally means that it's not matured 17 years and it's not yet out there. I'd like to see, I mean, some of it's been well over 17 years, so it's time for it to be out there. So if there are people out there that are in the dissemination business, there's a lot of stuff here that you could be disseminating.
Well, you should know that the hyperbolic tree is all over the place.
Yes, yes. Yes.
Hi, George. Thank you so much for your talk and congratulations. I'm Mario Romero from KTH, and like Gregory, I have a request and then sort of a discussion topic more than a question. The request is to please post that visualization of your career. It's fantastic. It's beautiful. I particularly loved the hurricane of corporate politics in the Mid-Atlantic or something like that. I enjoyed that one. And my suggestion or suggestion for a discussion, it goes back to Jacob's question, and it's the issue with the data mountain and the task gallery may have been ahead of their time by the limitations of the desktop, but they may be coming back with a vengeance with heads-up displays, augmented reality, and displays everywhere.
Yeah.
So, and it may be before those 17 years.
Right, right. Yeah, one thing we tried at Microsoft Research a little bit was that to kind of bypass getting things out through the product groups, which seemed to take a long time, we actually started posting some of our work directly on the web. One of the projects I didn't talk about was Scalable Fabric, which was another task management system, and that actually was put out and it's available on the web for anyone to download and use. I assume that's still out there. Yeah, and that one's been used by, Mary says, hundreds of thousands of people. So that's another way to get things out. So, yes.
Hi, I'm Nipun. I'm a UX designer at Samsung. And we do research also. And you said about the time frame for research should be between 5 to 10 years. I think it's even getting harder. Like, we are narrowing it down now, even probably smaller than 5 to 10 years because of the technologies of discontinuous or other disruptive technologies are come in much faster pace. What do you think? Like, is it going to be much worse in the future? Like, you won't be looking out further out than 1 year. In 5 years' time, you cannot just, innovate or, for stuff beyond a certain period of time.
Well, that's a good question. In my own experience, I don't see it those discontinuities happening more frequently, but maybe they are. I'm not sure what would be driving that. I think one way to measure that would be to analyze what's happening at the CHI conference each year and see how, are the changes that are showing up incremental changes, or are there some major new ideas that are appearing? That's one way to measure that. Yeah. I think we're actually past time, so I think we have to stop at this point, and thank you all very much.